Hello student, this is lecture 9 from our lecture series Advanced Materials for Energy and Information Technology. Here is the third part of the topic Critical Materials for Information. In this part we shall discuss about the storage materials. The earliest form of data handling and data storage was the punch card, discovered during 1725. Punch card is one of the oldest ways known to store information. It is a piece of stiff paper that contains digital information which is represented by the presence or absence of holes. Further, IBM developed punch card tabulation machine to record census data. It took 8 years to complete the census. Next in this direction was the punch tape, invented during 1846. A more advanced way of making punch cards were the punch tapes. It is comprised of longer connected stripes. Each row on the tape presents one character. Then came the selection tube, invented during 1946, an early form of digital computer memory but never made it to the commercial use. It was able to store up to 4,000 bits but ended up a short-lived, overpowered by other products in the couple of years. The next milestone is the magnetic tape, invented during 1951. The first commercial data tape which was used to record computer data on Univa. It was named Uniservo tape. Its data transfer rate was 7,200 characters per second, but it was made up of metal film which was very heavy to mobilize and to enlarge in capacity. During 1956, hard drive were invented. First hard drive was humongous and it was launched by IBM. Initially, it had the storage capacity just under 5 MB, but sooner IBM came up with gigabyte hard disks whose cost was 100,000 US dollars. Floppy disks were invented during 1971. First floppy was huge in size, that is 8-inch, yet it was very efficient. Later, the size of the diskette was reduced to 3.5 inches only. Laser discs were invented during 1978. It was first commercial optical disc storage medium. Further, the disc was very big, having a 30 centimeter diameter. However, it had the capacity to play radio and video files for 1 hour straight. The very next year, in 1979, came the compact cassette. It is used for audio recording and playback. Compact cassette was very famous during 80s for recording of computer data and for listening to music. During 1982, compact discs were invented. Compact disc is an optical disc used to store digital data. The format was not developed to store data initially. Moreover, the arrival of CD-ROM played a very crucial role in the success of CDs lately. During 1985, CD-ROM were invented. It is popularly used to distribute computer software. The device was initially slow and expensive. However, it managed to push away floppy disks by making CDs hold up to 4 GB of data, much more than a floppy disk. Then invented was zip drive during 1994. Iomega introduced zip drive in 1994 as a boon to the lower capacity of floppy, which was 1.44 MB only. Further, a higher quality magnetic coating was used in it. It could store up to 100 MB of data, which made it equivalent to the 70 floppies. DVDs were invented during the very next year, that is 1995. DVD was the successor of compact disc. Further, the transition from CD to DVD was much faster than floppy to CD. It is now considered as one of the most cost-effective means of portable storage. During the same year, ZES drives were also invented. Iomega launched this drive. It was similar to traditional hard drive. Further, it was able to store 1 GB of data, but it failed due to high cost per gigabyte ratio and due to the need of keeping the drive lying flat with the SCSI interface. During 1998, flash drives were created. It is considered as one of the remarkable inventions after the floppy disk era. It could store data from MBs to GBs. Its ability to trigger BIOS and to boot from USB key makes it superior over floppy. Flash drive also put an end to the floppy disk. After almost a decade, during the year 2006, cloud computing were invented. It is an incredible addition to the storage mediums. Amazon used the model first. However, Google coined the term cloud computing in 2006 during a meeting in San Jose. Moreover, it is considered as a revolution in the storage industry. Cloud complements tapes. Data tapes and cloud together are giving rise to the hybrid data storage strategies within the industry. During the same year, Blu-ray discs were invented. Relatively new in the market compared to CD and DVDs, it can hold up to 20 to 40 GB of data. It also looks similar to CD and DVD but functions through organic dyes. Soon after this, in the year 2009, holographic versatile discs were created. It is a new arrival in the CD market, which is designed for future use. Further, it could store 160 times more data than a Blu-ray disc, that is 3.9 terabyte on one disc. During the year 2000, an important advancement was recorded, that is SD memory. It was appeared on the storage scene during the early 2000s. It was initially able to store 32 to 64 MBs of data, which now has scaled up to 32 GB. In some of the SD memories, it can hold up to 64 GBs as well. The amount of data stored is measured in kilobytes, that is KB. Confusingly, 1 KB is actually 1024 bytes, not 1000, as you might expect, but most people think in multiples of 1000. Consequently, 1 megabyte, that is 1 MB, is 1000 KB. 1 gigabyte or 1 GB is 1000 megabyte. 1 terabyte is 1000 gigabyte. When a computer is first switched on, it needs to load up the BIOS, that is Basic Input-Output System, and basic instructions for the hardware. These are stored in ROM or read-only memory. This type of memory is called non-volatile because it retains the data. Data stored in ROM remains there even when the computer is switched off. ROM can be found on the motherboard. Computers store temporary data in the RAM, that is random access memory. These could be operating instructions, loose bits of data, or content from programs that are running. The contents of RAM are constantly rewritten as the data is processed. When the computer is switched off, all the data is cleared from the RAM. This type of memory is called volatile because it only stores the data whilst the computer is switched on. RAM sticks are found on the motherboard. The RAM stick is shown here in the picture on the left hand side. The primary types of magnetic storage devices are diskettes or floppy disks, hard disks, high-capacity floppy disks, disk cartridges, magnetic tape, magnetic strips on the credit cards. The 5.25-inch disk has a large circular hole in the center of the drive's spindle and a small oval aperture in both sides of the plastic to allow the drive's heads to read and write data, as shown in the picture here. The magnetic medium can be spun by rotating it from the middle of the hole. A small notch on the right of the disk identifies that it is writable, detected by a mechanical switch or phototransistor above it. Shown here are the floppy disk and the round disk. DD is double density, which contains 2 micrometer layer of magnetic iron oxide. The high density diskettes contain 1.2 micrometer of cobalt doped on iron oxide. The extended density contains 3 micrometer layer of barium ferrite. Magnetic storage or magnetic recording is the storage of data on a magnetized medium. Magnetic storage uses different patterns of magnetization in a magnetizable material to store data and is a form of non-volatile memory. The formation is accessed using one or more read or write heads. As we can see in the picture below on the right-hand side, the north-south direction of magnetic domains can be designated as 0 and 1, as in the binary language. The read head identifies the direction of these magnetic domains and decodes the data. On the left-hand side is shown the two kinds of recording layers. One is longitudinal recording and another is perpendicular recording. As the magnetic head or the ring, the writing element, passes across the recording layer, it rearranges the domains, that is the arrowheads. The similar way in the picture below is shown the magnetic head as it traverses through the recording layer, the direction of the arrows are rearranged and the data is recorded. In the same space, an additional layer can also be added so that larger amount of data can be stored in a smaller space of material. Magnetic storage media, primarily hard disks, are widely used to store computer data as well as audio and video signals. In the field of computing, the term magnetic storage is preferred, and in the field of audio and video production, the term magnetic recording is more commonly used. The distinction is less technical and more a matter of preference. Other examples of magnetic storage media include floppy disk, magnetic recording tape, and magnetic strips on the credit cards.
Magnetic memory, or magnetic data storage, is a key component in computer operation. This depends on the ability of magnets to magnetize other materials and the ability of those materials to retain their magnetization until forced to change again by exposure to another magnetic field. Furthermore, an object can be magnetized with the north or south pole at either end. You may already know that data is stored in computers in a series of ones and zeros, a machine language more commonly known as binary code. But how can we represent a 1 and a 0 magnetically? Let's take a look.
A bit is the smallest unit of data storage. It can be visualized as a minuscule block that can be magnetized into a permanent magnet. Every red, blue, or gray block in this picture is a bit. The red blocks have north poles facing up, and the blue blocks have north poles facing down. These are what the computer recognizes as ones and zeros. Gray blocks are the empty bits that have not yet been magnetized. The write head is basically an electromagnet, with a core appropriately shaped like this to direct the magnetic field into a bit and magnetize it as it passes by. It can magnetize a bit as a north facing up or a north facing down, simply by changing the direction of the current in the coil. As you may remember from the earlier sections, reversing the direction of current in an electromagnet results in reversing the direction of the magnetic field. Once written, the bits can be read by the read head, which senses the direction of the magnetic field as it goes over a written bit. A hard drive as a whole looks like this. Both the read head and write head are at the tip of the actuator arm. The motor of the disk and the motor of the actuator arm work collaboratively to align a desired bit with the read head or the write head at any given time to read it or write it.
A few years ago, an iPod of this size had the capacity of about 1 gigabyte. But now, a similarly sized iPod has the capacity of about 160 gigabytes. With each passing day, capacity just keeps growing more and more. But have you ever wondered how they can increase the capacity so many times without increasing the size? Let's take a closer look. As we have already seen, magnetics are an essential component to data storage. Research has led to additional applications such as magnetic logic, which will provide more efficient and effective ways of manipulating and storing data. Currently, computers are composed of 3 major sections: processors that control operations and manipulating data, random access memory chips, or RAM, which act as temporary data storage, and the magnetic disk drives that retain information even after power is turned off. Although computers are very complex, they're based on a combination of simple circuits called logic gates. A logic gate is a device that produces a specific output for a given input. There are several different types of logic gates. For example, a type of gate called an AND could be represented by a circuit with 2 switches and a light bulb which only lights up if the first and the second switch are on. If you were to replace the light bulb with a switch controlling the input to another gate, you would have the basis for a more complex system of interconnected gates. In today's computers, logic gates are built from electronic transistors. However, they can be built using many other materials. There are mechanical logic gates based on gears, electromechanical systems based on relays, and even ones based on individual molecules. A critical quality of any logic system is its speed. How quickly does a change in input result in a change in output? Magnetic logic systems can be very fast, and they have an advantage over transistor-based systems. They retain their information even after power is turned off.
The disk read-write heads are the small parts of a disk drive that move above the disk platter and transform the platter's magnetic field into electrical current, that is called read the disk, or vice versa, and transform electrical current into magnetic field, that is called write the disk. The different components of a read-write head and the diskette is shown here in the picture on the left. On the right hand side is shown a hard disk head and arm on a platter. Here is shown a microphotograph of a hard disk head. The size of the front face is about 0.3 millimeters. One functional part of the head is the round orange structure in the middle, the lithographically defined copper coil of the right transducer. Also note the electric connections by wires bonded to gold-plated pads. The heads are the devices made out of a tiny C-shaped piece of highly magnetizable material called ferrite wrapped in a fine wire coil. When writing, the coil is energized. A strong magnetic field forms in the gap of the C, and the recording surface adjacent to the gap is magnetized. When reading, the magnetized material rotates past the heads. The ferrite core concentrates the field and a current is generated in the coil. In the gap, the field is very strong and quite narrow. That gap is roughly equal to the thickness of the magnetic media on the recording surface. The gap determines the minimum size of the recorded area on the disk. Ferrite heads are large and write fairly large features. They must also be flown fairly far from the surface, thus requiring stronger fields and larger heads. The most advanced magnetic storage systems require about 1 million atoms to store a digital 1 or 0. The primary types of optical storage devices are compact disc read-only memory, that is CD-ROM, digital video disc read-only memory, that is DVD-ROM, CD recordable, CDR, CD rewritable, CD-RW, and photo CD. In this topic are included the types of backing storage. Computers need backing storage outside the CPU to store data and programs not currently in use. There are three main types of storage device. Those that store data by magnetization, a special material that coats the surface of a disk. Second, those that store data using optical technology to etch the data onto a plastic coated metal disk. Laser beams are then passed over the surface to read the data. And the third category is flash drives, which use solid state technology and store data in a similar way to the BIOS chip. The medium is what the data is actually stored on. Examples of media include floppy disks, CD-ROMs, and zip disks. The floppy disks hold about 1.44 MB of data. These are now largely obsolete or only available to some old instruments where the programs are still run by the floppy disk. The CDs hold around 700 MB of data. Zip disks store up to 750 MB of data. Nowadays, the zip disks holding higher amounts of data are also available. Next in the list of backing storage are the hard drives. The hard disk of the computer stores the system information, programs, and data that the computer uses every day. Computer servers will use RAID, that is redundant array of independent disk systems with many hard drives to provide huge capacity and safer storage. The drives can be mirrored so that the data written on one of them is also written to the others. So if one drive fails, the others just take over. Removable hard drives plug into the USB port and can be used for the backup or transfer of data to another computer. Some of the interesting facts regarding writing heads have been listed here. The read and write heads that operate very close, often tens of nanometers over the magnetic surface. The head detects and modifies the magnetization of the material immediately under it. There are two magnetic polarities, each of which is used to represent either 0 or 1. A write head magnetizes a region by generating a strong local magnetic field, and a read head detects the magnetization of the region. Electromagnetic heads are magnetic head creating the electromagnetic induction. Metal in gap MIG heads are the ferrite heads with a small piece of metal in the head gap that concentrates the field. Thin film heads are the fine features of MIG created by photolithography. Magnetoresistance MR heads are the one which changes the resistance of a material in the presence of magnetic field. Giant magnetoresistance GMR heads are one advanced variety in this category. Magneto-resistive reed element and thin film inductive Wright elements are the advanced versions in this category. Older hard disk drives used iron 3 oxide as the magnetic material, but current disks use a cobalt-based alloy. The magnetic surface is conceptually divided into many small sub-micrometer-sized magnetic regions, referred to as magnetic domains, mostly with uniform magnetization. Since the magnetic material is polycrystalline in nature, each of these magnetic regions is composed of a few hundred magnetic grains. Magnetic grains are typically 10 nanometer in size and each form a single true magnetic domain. Each magnetic region in total forms a magnetic dipole which generates a magnetic field. In older hard disk drives, the regions were oriented horizontally and parallel to the disk surface, but beginning about of the year 2005, the orientation was changed to perpendicular to allow for closer magnetic domain spaces. Comparison of several forms of disk storage showing tracks not to the scale, green donates start and red donates the end has been shown here. Blu-ray disc or BD is a digital optical disc data storage format designed to supersede the DVD format in that it is capable of storing high-definition video resolution, that is 1080p. The plastic disc is 120 mm in diameter and 1.2 mm thick, the same size as of DVDs and CDs. Conventional pre-Blue Disc XL Blu-ray discs contain 25 GB per layer, with dual-layer disc, which is 50 GB per layer, being the industry standard for feature-length video discs. Triple-layer discs are the 100 GB layers, and quadruple layers are 128 GB are available for BDXL read-writer drives. The name Blu-ray disc refers to the blue laser used to read the disc, which allows information to be stored at a greater density than is possible with the longer wavelength red laser used for DVDs. A magnetic stripe card is a type of card capable of storing data by modifying the magnetism of tiny iron-based magnetic particles on the band of magnetic material on the card. The magnetic stripe, sometimes called swipe card or magstripe, is read by swiping past the magnetic reading head. Magnetic stripe cards are commonly used in credit cards, identity cards, and transportation tickets. They may also contain an RFID tag, a transponder device, and/or a microchip, mostly used for business premises access control or electronic payment. A flash drive consists of a small printed circuit board carrying the circuit elements and a USB connected, insulated electrically and protected inside a plastic, metal or rubberized case, which can be carried in a pocket or on a keychain. The different components of a flash drive is shown here in the picture and listed on the right hand side. Secure digital or SD card is a non-volatile memory card used extensively in portable devices such as mobile phones, digital cameras, GPS navigation devices, handheld consoles, and tablet computers. It is a kind of solid-state storage medium. Inside every SD card, rows of tiny memory chips are at work, storing all your documents, music, photos, and more. And because there are no moving parts, it is all done quickly and effortlessly. The data on a SD card is stored in a digital format. The solid-state chip inside the card's plastic cover contains many tiny electrical circuits. When the card is not in use, the circuits retain their charges without any additional power. When a card is placed in an activated device such as a camera or a cell phone, a small electrical current from the device moves electrons in the flash memory chip. The digital patterns stored in the chip correlate to the data stored there. The data stored in the SD card is erased when a slightly higher voltage is applied to the circuit. This allows for rewriting. SD cards write and erase memory in blocks or sections. This makes them faster than some other varieties of data storage. SD cards meet legal requirements for storing content with copyright protection. Copyright protected works such as songs and books are written with a media identifier code. That code is placed on a protected portion of the solid-state memory. The copyright-protected work cannot be copied without access to that media identifier code. This keeps data from being copied multiple times and widely circulated without permission.
Memory chip design is the first step in the production of Micron's memory chips. This process involves the use of computer-aided design tools to lay out billions of electronic components that store data on the chip according to the product design specification. During technology development, specific process steps are defined and integrated into a process flow that will build the memory chips. The process steps are tested and refined until the process node is qualified and ramped in manufacturing. Individual memory chips, or die, are built upon pure silicon wafers in a fabrication area, or fab. Fabs are state-of-the-art clean rooms that are 100 times cleaner than a hospital operating room to ensure silicon wafers are protected from ambient contamination. Among the many process areas in a fab, the photolithography area coats wafers with a photoresistant material. Then, like film in a camera, circuit patterns are exposed and excess material is rinsed away. The paths in these circuits are 5,000 times narrower than a human hair. Wafers are moved between different tools and processes using a robotic automated material handling system, or AMHS. Each wafer may be moved through more than 1,000 processes. It takes more than 1 month to make a memory chip. In probe, initial functionality tests are performed on each die on the wafer. A probe card positions probe needles onto each die to send and receive test data. This information is used to generate a map of all the die on each wafer. Only good die that pass all tests in probe will continue through the manufacturing process. In assembly, wafers are first thinned, attached to an adhesive backing, and then diced into individual die using a diamond-edge saw. Using the wafer map that was created in probe, individual die are picked from the wafer, then placed on a circuit board. A solid gold wire is used to connect each chip to the circuit board. A A molding process encapsulates each die in a protective plastic package and shipped to test. Every memory chip Micron manufactures undergoes hundreds of tests to ensure it meets the highest quality standards. Proprietary Ambix testers subject finished parts to extreme temperatures and conditions to force any weak components to fail before they reach our customers. Additional test equipment verifies that each part meets or exceeds its speed and performance specifications. All qualified parts are laser marked with part numbers and other identifying information. Each memory chip is optically scanned to verify strict fit and form specifications. Components are placed into industry-standard anti-static packaging and placed into boxes for shipment. Many of Micron's finished parts are used to build memory modules and solid-state drives. Automated surface mount assembly equipment is used to mount memory and other components to printed circuit boards. All products are tested using proprietary Micron memory module and SSD test equipment. Finished products are placed into anti-static packaging before boxing for shipment to the customer.
Here in this picture shown a simplified way to explain the decrease in silicon transistor size over the years from 1960s through 70s, 80s, 90s, 2000s and 2010, where it decreased down from a unit size to 1/1,000,000th of the size. Current silicon transistor storage technology size has continued to shrink and will approach to atomic level sometime. The previously designed most advanced magnetic storage systems, which required about 1 million atoms to store a digital 1 or 0, that is 1 bit of data, IBM researchers have now successfully used 12 atoms to store 1 bit of data by aligning their magnetic properties so that the group of atoms would not interfere with their neighboring group of atoms. So now 12 atoms are needed to store 1 bit of data. What does this mean for potentially storage density? Today's memory technology is shown here as 100 magnetic memory disks. The atomic scale magnetic memory is potentially 100 times denser than today's hard disk drive technology. That is, one atomic scale magnetic memory could store as much as of data as the previously designed 100 magnetic memory disk. would contain.
At IBM, we are interested to understand how the magnetic properties evolve from the individual atom to something that might be useful for a technology for data storage. We as an industry have been following for many years this trend that we now call Moore's Law, where we exponentially shrink the components down by a small factor every year. Now what we are allowed to do in this laboratory here is we're allowed to jump to the ultimate end and start with single atoms and build structures one atom at a time. In this breakthrough, what we have done is we have stored magnetic information in only 12 atoms. We have this specialized tool that allows us to investigate the properties of single atoms and small clusters of these atoms. And now for the first time, we've actually seen that these 12 atoms behave like a stable magnetic unit. So a current computer hard drive, for example, stores information in a large number of magnetic atoms. And all these magnetic atoms act together to make one bit of magnetic information. And so if we can scale down, then we correspondingly get a much larger density or much larger number of bits in our disk drive or in our computer. Here you see a representation of a single magnetic bit consisting of 12 atoms that we built with the scanning tunneling microscope on this surface. The tip of the scanning tunneling microscope can also be used to switch the magnetic information on this bit from a 0 to a 1 or from a 1 to a 0. Now we're zooming out from the single bit to 8 bits, which makes 1 byte, which is the next bigger unit of information in a computer. A byte, for example, can store all the characters that you have in the alphabet and all the numbers that go with it. If we zoom out further, then you can see that we can put many of these bytes next to each other. In this example here, we have 5 of those, and they store different information in them. In this case, the letters T, H, I, N, K. In this size comparison to existing technology, you can appreciate how much smaller this atomic scale magnetic data storage could be and how much more information you could store in the same space on your drive.
So this is actually a testament to IBM's investment in R&D. IBM did not become a 100-year-old company by doing the same thing over and over again. We're constantly innovating, and in fact there is so much encouragement to innovate. This has become a place where the innovation engine is very, very vibrant. And what you're seeing here today is one of many outcomes from our investment in research, long-term investment in research. And so we are actually very proud to kind of showcase our ability to invest in research, and then from time to time we get this opportunity to show the world what investment in research can bring to a company.
This brings us to conclude the part 3 of this topic. Now let's continue to the part 4 of the topic.